All right. Well, I know it's been a couple weeks since I've seen you guys. Does anybody remember what we talked about 2 weeks ago? Well, I think we had a test before break, so if we go back over all this stuff, we'll have to talk about basically we were talking about groups, subgroups, and how to find subgroups, different things like that. And so we're going to pick up there, and what we're going to do now, instead of finding subgroups, we're actually going to generate groups or generate subgroups, or we're going to use direct products here, which means we'll make new groups from old groups. And so we'll go ahead and get started with that. The first thing I want to put out here is to remind us, if we let G be a group, then what I'm going to say is that the group or the subgroup generated by an element A, which is written as in the PowerPoint there, is going to be the set of all the elements of the form a to the n such that n is an integer. So we're going to say that this is the group generated by A. Hello there, I hear you in Discord. So a group generated by a single element we're going to be calling a cyclic group. And what I want to point out here is I want to point out that a to the n can be infinite. Otherwise, if it's finite, there will be a smallest n such that a to the n is equal to a to the 0, or the identity in the group G that we started in, and we're going to call that n the order of A. What I want to do is just look at this and then say, let's make sure that if I have A as an element in a group, it would have to, the group generated by that would look like what I claimed it did, and that if it's a finite group, it's going to end up like I claim it did, where some a to the n is equal to the identity. So the first thing to point out is that notice that A is in my group. So what were the properties of the group? Do you guys remember those? That's fair. It's it's been a long time since we talked about this, so I wanted to bring this up to remind us. And so the properties of the group were that one, we had to have a closure for the binary operation. So whenever we multiply, we end up back in the set. Two was we had associativity. Three was we had an identity. And four was we had inverses. All right. So since it has to be closed under products, what we're going to get is that if I take a times a, it's going to be in there, but a times a is a squared. A times a times a is a cubed. So a to the fourth, a to the fifth, a to the sixth, and so on. And so what we're going to get is that a to the n for any natural number n is going to be in my group generated by a, because we have to be closed under the multiplication. Now we also have to have inverses. So if I write a to the negative 1, by that I mean the multiplicative inverse of a. So the multiplicative inverse of a has to be in there. And so a to the negative 1 has to be in there. But if we multiply those, we get the identity, which a to the 0 then is just going to be our identity, because it is a to the negative 1 times a to the 1 is a to the 0 is e. Further, if we multiply a to the negative 1 times itself a bunch of times, go ahead, T. So what we have is that a to the 0 is always 1 for the real numbers, and so the identity for real number multiplication is going to be 1. That is correct. However, in general, we don't have to deal with the real numbers, and we don't technically have to deal with multiplication either. So if this was addition, then when I say a squared, what I really mean is a plus a would be 2a. So when I say a to the 0, this would actually be 0, because that would be negative a plus a. And so in general, when I'm writing out a to the 0, it isn't necessarily 1 because we aren't necessarily dealing with real numbers. If we are dealing with real number multiplication, then yes, this would be 1. But what I am trying to point out is that a to the 0 has to be the identity, because a to the 0 is a to the 1 times a to the negative 1, or a inverse. And a inverse, the inverse is defined so that the product of a and a inverse is the identity. So while it doesn't have to be 1 per se, it does always have to be the identity. And so what we see here is that you are welcome, T. Thank you for asking such a wonderful question. But what we see here is that if we find the group generated by A, then all powers of A will be in that group because it has to be closed under these properties. Now, also, if we close under all of these things, we notice that we will indeed get a group because a power of A times a power of A is again just a power of A. So A to the, so for example, A to the 5th times a to the negative 6th is a to the negative 1 is, again, we have integer exponents. When we multiply, we add the exponents, so we end up with an integer. So in general, if we took something like a to the k1, a to the k2, we get k1 plus k2. And since k1 and k2 are integers, again, we get a to an integer. So that group that I talked about, a to the n such that n is in Z, is indeed going to be a group. Now, if, in fact, each one of these is distinct, then what I get is that I will have infinitely many elements in the group generated by A. And in particular, what we're going to get is that this is going to be a lot like the integers, because if I take a to the 1 times a to the 1, that's really just 1 plus 1 is 2, or a squared. And so it's going to behave a lot like the integers. And so if I say a cubed, I say 3. And then I say negative 1. 3 plus negative 1 is 2. Well, a cubed times a to the negative 1 is a squared. And so a cyclic group with infinitely many elements is going to look just like the integers. It'll look a little bit different, but it's going to behave just like the integers, where if I take a to the 5th times a to the 7th, well, I just add 5 plus 7 is a to the 12th. What can happen, though, is that we can get that this is finite, and that is that we get some repetition. And so let's say a to the n is equal to a to the m, with n not equal to m. Now, I just said if this doesn't happen, that is, these are never equal when these are not equal, then we get something that looks like the integers, and it's infinite. So the only way it can be finite is if this were to happen. So if this were to happen, what I want to know is what would that imply, and what would my group have to look like? Well, what I want to point out is now, if I multiply both sides by a to the negative n, what I get here is a to the negative n times a to the n is just the identity, or a to the 0. And on this side, I get a to the, we'll say, m minus n. So what I have is that in a group, if I am finite, I have to have some a to the n equal to a to the m for n not equal to m. Therefore, a to the 0 has to be equal to a to the m minus n, or that is, a to the 0 is equal to a to the k for some integer k. Now, since that's going to happen for some integer k, what I can do is I could say, well, it'll then have to happen for some positive integer as well, because if I take, oh, I'm knocking my chalkboard down because I leaned on it. All right, so if m is bigger than n, we get a positive number here. If n is bigger than m, then we can go the other direction. We would say a to the negative 0 is a to the negative m plus n, but a to the negative 0 is just 0. So we can find a positive integer or a natural number such that a to the 0 is equal to that k. But I just want to point out what that means is that I can say that a to the k is equal to a to the 0 for some k. And if I take all of the elements such that a to the 0 is equal to a to the, let's say, s, then what I notice is that, okay, well, m minus n has to be in here, or negative m plus n, depending on which one's positive. And so if I take all the ones smaller than that, then what I'm going to end up with is, well, all of these that I'm going to talk about is a set of all a to the s such that a to the s is equal to a to the 0, and s is less than or equal to k, and s is a natural number. We know that this is a non-empty set. It also has to be finite because at most we have k elements here. So if we have a finite non-empty set, it has to have a least element. Hence, there has to exist a least element such that a to the k is equal to a to the 0. Therefore, if we can find that least element, that we're going to call that the order of a. And in fact, that's going to be precisely equal to the size of the group generated by A. So just as a note, let's suppose a to the k equals a to the 0, and k is the smallest such element. Well, then I know that my group has to have a to the 0, a to the 1, a squared, a to the k minus 1. Notice a to the k would just be a to the 0, so we don't have to rewrite it. And each of these would be distinct because if, say, some other ones were equal, a to the I is equal to a to the j, then a to the j minus I is equal to a to the 0. But I said that k was the smallest one, therefore j minus I, this would be smaller than k, therefore it would have to be equal to 0, therefore I would have to be equal to j. So the only way a to the I is equal to a to the j is if I is equal to j. Now, if I take something else outside of this set, like a to the m, remember I can write this as a to the q times k plus some remainder with 0 less than or equal to r less than k using the division algorithm. But this is a to the qk times a to the r, which is a to the k to the q times a to the r. But a to the k is the identity is anything is the identity, so I get a to the r. So the point I'm trying to make is if I take any element of the form a to the m, I can rewrite it as being equivalent to one of the elements between a to the 0 and a to the k minus 1. And in particular, it's going to be the one where m is congruent to r mod k, because when I use the division algorithm by k, I'd have a remainder of r. And so what we're going to see is that if I find a cyclic group or a group generated by one element, if it's infinite, it's going to look like the integers. Whereas if it's finite, there's going to be the smallest k where a to the k is equal to a to the 0. I'm going to have exactly k elements then. And all of the elements are going to perform like the integers mod k. Because if I took something like a to the second a to the k, I would get a to the k plus 2, but a to the k is the identity, so I get a squared, or a to the second times a to the k minus 1 is a to the k plus 1, so I'd end up with a if I multiplied those two together. So what I get is basically the integers mod k. So when I have a cyclic group, they're going to end up looking like this form, and they're either going to look like the set of integers or they're going to look like the set of integers mod k. Does that make sense? Did you guys follow that one? So T asked if it's normal, not understanding it the first time, and yes, that is completely true. So the nice thing about this is that you guys can rewatch this if you want. And I hope you do, but I'm trying to just point out, at least in theory, I hope you're understanding that what I'm trying to say is that either I have a cyclic group, which means it's generated by a single element, then it's either going to look like the integers or it's going to look like the integers mod n. I actually wrote a post out for this one giving the complete proof of it, if you'd like to read through that too. But I kind of wanted to have a starting point to say, what do cyclic groups look like? What can we do with cyclic groups? And so if I have A, it's the cyclic group generated by A is just all the powers of A. Sorry, go ahead. So if I'm finding a cyclic group, I don't know which one it's going to end up looking like. It would depend on what group G I started in or what the powers of A look like. So if I start with, for example, the real numbers and I find that a group start generated by 1, I'm just going to get the integers. But if I look at a different group, like the integers mod 4, I could find the group generated by 2 is going to consist of 2 and 0. So it's actually going to look like the integers mod 2. And so depending on the group that we're starting in, we'll have different properties about A on whether or not it will generate an infinite number of elements or a finite number. And if a finite number, how many elements is it going to generate? But once we know if it's infinite or if we know if it's finite and what the order is going to be, we can tell what the group's going to look like. Does that make sense? All right. All right, good. So what I want to do is I want to work with that a little bit. And so here I'm going to say that if C denotes the collection of any subgroups of G, then the intersection of all those groups is again a subgroup. So let's think about, what does that mean? Well, it means if I take a bunch of subgroups of G and I find the intersection, which is the stuff that's in all of them, this will also be a subgroup of G. All right. Let's actually look at that one. Let you guys think about that as I'm setting up here. So let's give these things names and let's call them A sub I such that I is in I. And what I want to do is find the intersection of all these things. Each of these is a subgroup of G. And so what I want to show is that this is a subgroup of G. So the intersection of all of these subgroups is again going to be a subgroup. So now a point here is that if I have a bunch of if I have one element, how do I find the subgroup generated by that one element? Or on the other hand, if I have a bunch of subgroups, can I find a new subgroup, which is the intersection of all of those? And if I want to find the intersection of all of those, that means just all the stuff in all of them. So let's see if we can remember it. Do you guys remember from like way back 2-3 weeks ago? How do we determine if this is a subgroup of G? Very good, T. So I have to show that the intersection of each of these is not empty. Then I also have to show what else? All right. So I was writing that out as T was saying it. So the point is we have to show that the intersection of these is not empty, so that this set is not empty. And we have to show that for any two elements in my set, which I'm calling the intersection of these, then the product of A and B inverse is going to be, again, in that set. So what I'd have to do is, first off, find something that's in the intersection. So maybe you guys can help me out here. Each of these is subgroups of G. Is there something that has to be in each of these? Yes, T. What element is that? So in order to be a subgroup, it has to be a group, right? So in order to be a subgroup, it has to be a group. So therefore, the identity has to be in each of these, but the identity of the subgroup is the same as the identity of the group. So the identity of the group G has to be in each one of these. So that is, to write it out, we know that the identity in G is in A sub I for all I, because it's in any subgroup of G. Therefore, the identity is an element of the intersection of all the A sub i's. Does that make sense? All right. So we know that the identities in each of these. That's exactly right. Showing that the identity is in all of these elements shows that the intersection is not empty. And we know that the identity has to be in each of them because each of them is itself a group. All right. Now what I want to think about is if I take A and B in the intersection, what does A and B inverse have to be in? Well, notice that A is in A sub I for all I, and B is in A sub I for all I. Therefore, B inverse is in A sub I for all I. But each of these A sub i's is a group. Therefore, the group is closed under inverses. It's closed under the operation. So this again has to be in each A sub I for all I. That is, I know A is in A sub I. A is in the intersection, so it has to be in each of the A sub i's. B is in the intersection, so it's in each of the A sub i's. Therefore, AB inverse is in A sub I for each of the A sub i's. So AB inverse is in there for all I. Therefore, it has to be in the intersection. Hence, by our subgroup test, we get indeed that the intersection of any collection of subgroups of a group will indeed be another subgroup, which is kind of neat. It's just arbitrary intersections. I didn't even say anything about finite intersections here, just arbitrary intersections. I can take the intersection of as many groups as I want, and I still get a subgroup of my original group. All right, so now to illustrate that a little bit more, exactly what's going on, let's go ahead and find both some cyclic groups and intersections. So let's start off with, I want to change my screen here, sorry about that. So I want to find some subgroups and cyclic groups. Oops. And so let's find the group within the set of integers. So we'll have G be the set of integers. I want to find the group generated by 3, the group generated by 4, and then I'll find the intersection. So I'm going to use the integers with addition because it needs to be a group. So I'll let you guys think about what would the group generated by 3 look like. So it'd be A0, A1, A2, A3. But now, because I'm using addition, I'm going to use my addition notation. So I would have basically 3 times 1, 3 times 0, 3 times -1, 3 times 2, 3, 4. And so if I want the group generated by 3, so the group generated by 3 is really just going to be 3 times 1, 3 times 2. So this is actually just going to be all the things of the form 3k such that k is an integer. So the group generated by 3 as a subgroup of the integers is just going to be all multiples of 3. And so it's going to look like this. Does that make sense? Is that going to be infinite or finite? So now, if I was using product as my thing, that's the notation I would use. But here, if I say something like 3 squared, what I really mean is 3 times 3. But now my operation is the normal addition. So it's 3 plus 3, which is 6. So we were using multiplication notation before, and here I'm just saying, okay, my operation is addition. So when I really say 3 squared, what I really mean is 3 operation 3. So 3 operation 3 is 3 plus 3 is 6. So 3 squared was technically 6. And then, so if this is a and a cubed is actually 3 plus 3 plus 3 is 9. And so that's kind of the point I'm trying to make here is if I change the operation, it can look differently, but it's still going to behave the same way as we're going to get the generating element, and we're going to compose it with itself through the operation however many times. Since here my operation is addition, I can add it however many times I want or subtract it however many times I want. So I end up with the multiples of 3. Does that make sense? All multiples of 3. So we'd also get 12, 15, 18, and so we would actually end up with an infinite set here, right? All right. To go back to my earlier point here, as I said that because this is infinite, this should actually just look like the integers. And notice that with a relabeling, this would look like an integers because if I treat these things, well, I have 0. If I treat this like a 1 and a 2 and a 3 and a 4, well, then 3 plus 6 is, or 1 plus 2 is 9, which is 3. And so if I kind of think about these as 1, 2, 3, 4, it's going to behave the same way as if I think about this as 3, 6, 9, 12. So we're actually going to get something that looks a lot like the integers with just a different labeling. So that is what I'm trying to point here is that the multiples of 3 behave just like the integers under addition. And I think we've notated these as 3z before, so I'll write that down. So the group generated by 3 is 3z. All right. I also wanted the group generated by 4. So what is the group generated by 4 going to look like? That's going to follow the same process, right? So it's just going to be the multiples of 4. So we get 4z is the group generated by 4. Now, the next question would be, what is the intersection of these two sets? Now, what is the intersection of these two subgroups? Well, I'd have to find the things that are in both of them, right? So if I want to find the things that are in, exactly right. So we're going to want the things that are both divisible by 3 and divisible by 4. Sorry, just trying to mess with my thing so that I can see. So things that are divisible by 3 and divisible by 4, you're claiming are the things that are divisible by 12, right? So the claim here is that this is going to be 12, or the group generated by 12, which is 12z. Makes sense? Now, that's the claim, and that's a very good guess. But if I wanted to prove this, what would I have to do is I'd have to show everything in here is also in here, and everything in here is in here, right? So how would I prove that? Well, starting this way, if I'm in 12z, I'd have to show that it ends up in here. So if I'm in 12z, I'm a multiple of 12. Am I necessarily a multiple of 3? Well, 12 is 3 times 4, so if I'm a multiple of 12, I have to be a multiple of 3, right? And if I'm a multiple of 12, I have to be a multiple of 4. So therefore, what we just shown without having to do too much work is that this is indeed a subset of this. But if I want to show equality, I have to show that this is a subset of this. So I actually want to do that proof. So I'm going to say that 3 intersect 4 is a subset of the group generated by 12. And so what I'm going to do is let A be in the intersection of these two. And I have to show that then A is in the intersection, or in the set of multiples of 12. So here we're setting up this proof. Since it's in here, that means that A is equal to 3k1 and A is equal to 4k2 for some integers k1 and k2. And what I have to show is that A is actually equal to 12k3 for some k3. All right, so how do I get from here to here? So now if I try to look at this, very good. So if I do this and I do take a squared, I do get 12k1, k2. So I know that a squared has to be in there, but I don't necessarily know a has to be in there. And if I try to take just a is 3k1 and a is 4k2, but knowing that doesn't really help me out all that much because I want to multiply them to get 12, but I can't do that because then I end up with a squared. So what I have to do here is I actually have to be a little bit more creative. And what I notice is that 3 divides a. So 3 divides 4 times k2. So I'm going to need to use that. And the reason why I'm going to need to use that is because that's going to allow me to get this out. But what do we know about 3? 3 is what kind of number? It is a prime number. It is odd. But the important part here is actually that it's going to be a prime number. And what do we know about prime numbers? I know it's been a long time, but we know that if a prime number divides a product, it has to divide one of the terms of the product. Therefore, since 3 divides 4k2, 3 either divides 4 or 3 divides k2. Does 3 divide 4? Let's see. 4/3 is not an integer, so 3 does not divide 4. So 3 divides k2. What that means is that k2 is equal to 3k, I think I'm up to 4. And so what I can do now is I can use that to get a is equal to 4k2, which is equal to 4 times k2 is 3k4, so I get 12k4. So now this isn't as clear to show that this is a subset of this. What we had to do is we had to realize that, well, I know it's divisible by 3 and 4, but because it's divisible by 3 and 4, I know that a is equal to 4k2. This is divisible by 3, but since 3 does not divide 4 and 3 is prime, it has to divide k2. Therefore, we have to get that it's going to be equal to, or we have to be able to plug these together, and we will in fact get that it will be the group generated by 12. And so we'll get the group generated by 3 intersect the group generated by 4 will indeed be the group generated by 12. Now, I'm going to leave this as an open question, but if I take the group generated by m and n, is this equal to the group generated by m times m? Because that's what we had, 3 and 4. 3 times 4 was 12. Is that going to be true in general? Well, no, it's not. Because if I try the group generated by 2 and the group generated by 2, it is not the group generated by 4. So something else is going to have to change here. It's not just going to be n times m, but rather what it will end up being will be the least common multiple of n and m. And now we would have to prove that. But I'm going to put it up there for kind of future reference, and we may get to that later. But I'm just going to point out it's not quite just n times m, but it is the least common multiple of the two. All right. And so what we're going to say is that if we have S is any subset of G, so if I have a group, I'm going to say that the group generated by S. So notice here we did the group generated by a single element. We can also do the group generated by an entire set. What we're going to say is that that's going to be the intersection of all groups that contain S. So that is, it's going to be the smallest subgroup of G that contains the set S. And so we're going to call this the group generated by S. So what we would do here is you could find all of the groups that contain S, and so you would find then the intersection of all of these, and therefore the intersection of all these will be a group because each of those were grouped. Since the intersection is smaller than any containing part, it therefore will have to be the smallest group containing S. So there will have to exist a unique subgroup of G, which is the smallest subgroup containing S, and so that's what we're going to call the subgroup containing by S. All right, so with that, just to kind of give it context, in Z again with addition, what would be the group generated by the set 3, 4? So I know I have 3 in there, and I have to have 4 in there. Now when I find the group generated by this, I mean the smallest subgroup which contains both 3 and 4. Well, I know that I'm going to have all multiples of 3 because 3 is in there, so that's going to generate those elements. The 4 is going to be in there. The 12 are... Oops. Thank you, T. I have to change the screen. I keep forgetting to do that one. All right, there we go. So the group generated by 3 and 4. I know that I'm going to have multiples of 3. I know I'm going to have multiples of 4. I know I'm going to have multiples of 12 because that's the intersection of these two, right? And so I know that at least 12z will be in there, and 12z is smaller than these two, so I know that this would be a smaller group. What I want to know is, can I find an even smaller group, though? So 12z is in there, all multiples of 12. So now, actually, I should be careful here, as I know that if I'm generating it, I have to have these and I have to have these, but I want to find the smallest group containing 3 and 4. Does 12z contain 3? Sorry, that should be my question. Does this contain 3? Well, the 3 is not a multiple of 12, so this would not quite work. And then notice that this group wouldn't work because it doesn't contain 3, and this group doesn't work because it doesn't contain 4. So what I have to find is the smallest group which contains both 3 and 4. And so if I'm trying to add those in, I would have to add these in. I would have to add these in. All multiples of 3 will be there, all multiples of 4, all multiples of 12. But those are going to keep getting added in to make a bigger group because I have to contain at least these two elements. So I want to find the smallest group containing both of these elements. So what I have to think about is not only are 3z and 4z in there, but I could also do something like 3 plus 4 would have to be in this group. So 7 has to be in there, so the multiples of 7 have to be in there. Does that make sense? Now, actually, if we skip to the punchline here, what is 4 minus 3? I think 4 minus 3 is 1, right? So what I know is that 1 has to be an element of this, doesn't it? All right. So if 1 has to be an element of this group, then the group generated by 1 has to be a subgroup of the group generated by 3 and 4. Why would that have to be the case? Is, well, if 1 is in here, then that means that the group generated by 1 has to be in here. And so that is exactly right. Because we have 1 in here, we're going to get the entire set of integers, and so I get the integers is a subset of 1, which we just claimed was a subset of this, but this is a subset of the integers because these is the group generated within the set of integers. So what we end up with is that these are actually going to be the group generated by both 3 and 4 is indeed actually going to be the set of all of the integers. And as someone stated, that's because they're going to be coprime, because there is no greatest common divisor I can find, or because the greatest common divisor is 1 rather, I can find something where I get out a 1, so then I'm going to get out all of z. Do you guys see that working out? All right, let me change the screen back real quick. And so, let's do... what I have here is that if this was something where they have a common divisor, let's just do 2 and 4. Then what's going to happen here is, what is the greatest common divisor of 2 and 4? I think it's 2. So I would think that this is actually going to be the group generated by 2, which is 2z. Also, if you did 4 and 6, the greatest common divisor is 2. So I would think that these would have to be equal. Now, in order to show that, let's just say I have A and B. I claim that this is the greatest common divisor of A and B. I think I have that later in the thing, the PowerPoint, but let's just do it now. How would I show that the group generated by A and B is equal to the group generated by the greatest common divisor of A and B? Is I have to show that everything in here is also in here, and everything in here is in here. So the first thing I'm going to show is that everything in here is in here. So this is a subset of this. So let X be in the group generated by A and B. What is X going to look like? Well, because these are within the set of integers, it's going to be a multiple of A times, so let's say K1, plus a multiple of B times, say, K2, because I have to close this under. So if I take the set generated by two things, I have to close this set, and so I'm going to get closure for products and inverses for A is going to give me A times K for all integers. Closure for B is going to be B times K for all integers. And then because I have to be able to add those, I would have to take something like this and add something like this. Are you guys following me there? If not, just to recap, if I have the group generated by two elements, I'd have to have the group generated by each one individually. But then I'd have to be able to add any of those two elements together, and that would close it. And now I do have a group, and I could show this is in group because I could take something in here plus the inverse of that, and I would get something back in here. So this is indeed the smallest subgroup containing these. So X would have to look like this if it's going to be in the group generated by these two. But notice that this part's divisible by the greatest common divisor, and this part's divisible by the greatest common divisor. So if this part's divisible by the greatest common divisor, and this part's divisible by the greatest common divisor, their X is equal to, let's say, K3 times the greatest common divisor plus K4 times the greatest common divisor, which therefore is equal to K3 plus K4 times the greatest common divisor. Therefore, X is indeed in the group generated by the greatest common divisor. So if we're in this group, we have to be in this group. Now, the next thing I want to point out to show the other direction. Yep, I do have to prove that the other way. To show the other way, what I want to do is I actually want to use something that's going to be on the next slide of the PowerPoint, is that if I can show the generating element of this group is in this group, then this has to be a subset of this. And so what's going to happen here is, even if this is multiple elements, if each of the generating elements are in this group, then this will have to be a subset of this. Now the reason being is because if this is in here, in this group, well, this is a group, so it's closed. So anything generated by that element would also have to be in here. So therefore, if I can show the greatest common divisor is in here, then the entire group generated by that has to be in here. So instead of having to show that any arbitrary element is again in this one, I really just have to show the greatest common divisor is in this one. So I'm going to save a little bit of work for me there. Are you guys following that? So that is, if I'm trying to show that A is a subset of just any group A, if A is in A, I know that A is a group, and this is the smallest group containing A. Therefore, that implies that A will have to be a subset of A. So if I can show that the generating element here is in this set that I'm trying to show this is a subgroup of, well, since this is the smallest one containing A, necessarily this has to be contained in A. All right. So what I want to show is that the greatest common divisor is in here. Well, what do we know about the greatest common divisor is that, I don't know if you recall this, but we proved that I can take an integer k and an integer l, and I can write ka plus lb is equal to the greatest common divisor of ab. Now, I know this is going back a little bit. I'm not going to take the time to reprove this, but because we had to do this using the Euclidean division algorithm, and we got out, we found the greatest common divisor, and then we showed that this would actually have to be true. So it took a while, but we were able to show this. But now, because we have this, what we get is that an integer times a is going to be in my group generated by a, and the integer times b is going to be in my group generated by b. Therefore, if I add them, it's in my group generated by a and b. Therefore, this element is in here. And because the generating element is in this group, that means the group generated by this element has to be in this group. So this is a subset of this. And we will indeed, in general, get 4 integers. The group generated by AB is exactly equal to the group generated by the greatest common divisor. Any questions on there? All right, and so actually that's what this slide says, is that if we have T1 and T2 are subsets, and I'm going to show that the group generated by T1 is equal to the group generated by T2, that is for any sets, I can just show that the set T1, every one of those elements is in the group generated by T2, and all the elements of T2 are in T1. So I don't have to do a complete proof that all the elements of each group are in the other. I just have to show the generating group, or generating elements, are in the other group. And so that'll save us some work and some time as we're going through proofs trying to show that groups that are generated by things are the same, is we can just focus on the generating elements. So for example, I want to show that in S4, 1, 2, 4, comma 2, 3, 4 is equal to the group generated by 1, 2, 4, 1, 2, 3, 4. All right, so how would I do that? Well, I had 1, 2, 4, and 2, 3, 4. And I want to show that it's equal to the group generated by 1, 2, 4, 1, 2, 3, 4. So if I want to show these are equal, instead of having to show that everything in here is also, so I don't have to make a full Cayley table. However, if you want to make a full Cayley table, you can. But I want to show that everything in these two things are in this group, and these two things are in this group. So I don't have to show everything in here is also in here, and everything in here is also in here. I just have to show the generating elements are in the other ones. So if I want to show this direction, what I have to show is that this is in here and this is in here. So for that proof, I'm going to say, first off, let's start with the easy one. Is 1, 2, 4, let's call this A and B just so I don't have to write these over and over again. Is this in B? So I'm trying to show that 1, 2, 4 from A is also in B. That has to be true because that's by definition, right? So we don't have to do anything there. So we could just say check and we'll move on. Now we have to show that 2, 3, 4 is in B. So that's going to be the hard part, of showing this is in B. If we get that, then we know that A is a subset of B. So what I have to do is, and you may have to make a Cayley table for this, but you have to write 2, 3, 4 as the composition of 1, 2, 4, 1, 2, 3, 4 any number of times. So I can use 4 of these or 5 of these and 6 of those and in any order I want, but somehow I need to get this out. So what I would do is just actually take the composition of these two and see what happens. So I'll write that up here. I'm trying to get this one out. Let's just take 1, 2, 4, composed with 1, 2, 3, 4. So if I look at this, 1 goes to 2, 2 goes to 4. So we get 1 goes to 4. If I get 2 goes to 1 goes to 2. I'm sorry, I'll start with 4 goes to 3, which stays at 3. And then 3 goes to 4 goes to 1, so I'd close this off. 2 goes to itself. So if I compose these two, I get 1, 4, 3. So it's not quite what I wanted because I wanted to get 2, 3, 4, right? So is there some other way I can do this so that it would work out as 2, 3, 4? I don't know, I'm going to try the other direction and see what I get. Yeah, so let's try that. So if I start with 1, 1 goes to 2, 2 goes to 1, so I get 1 goes to 1. On the other hand, 2 goes to 4, goes to 3, so 2 ends up at 3. And then 4 goes to 1, goes to 2. I'm sorry, I had 3 next. 3 goes to 4, and then 4 goes to 1, goes to 2. So if I do that in the other direction, that is this one composed with this one, I get exactly what I was looking for, 2, 3, 4. So that means that 2, 3, 4 is equal to the composition of these two. Therefore, it's in the group generated by those two. Therefore, we have now proven, just by showing those two elements are in there, that A is a subset of B. Do you guys see that one? All right. Now to show the other direction. Yep, go ahead. So going to this, 1 goes to 2. So we start over here. And we move here. 2 goes nowhere. But then 2 goes to 1. So we end up with just 1 goes to 1. So we started at 1. We ended at 1. So I'm going to start with 2. 2 went to 4. But moving to the next one, 4 went to 3. And then moving to the next one, there's no 3. So I just end up with 2 ended up at 3. And if I continue, I'm going to start at 3. 3 goes nowhere. 3 goes to 4. 4 goes nowhere. So 3 goes to 4. And then I'm going to go 4 to 1. There's no 1, so I don't do anything. And 1 to 2. So 4 ends up at 2, and we end up closing off that cycle. So we just get 2, 3, 4. Is that clear? Good. We're going to need some practice again with these because it's been a while and it is weird reading them from right to left, but also left to right within them. So that'll come back to you guys as you're doing the homework again. Just make sure to start, looking at those and getting used to that all over. All right. To go the other way though, I know that 1, 2, 4 is in here because it's given, but what I want to do now is show that this is going to be in this group. So I have to show 1, 2, 3, 4. is going to be an element of the first group. So I have to write it as a composition of these two any number of times. So what should we try? Sure. So let's try 1, 2, 4, composed with 2, 3, 4. Let's just see what we get. 1 goes to 2. So there's no 1, then 1 goes to 2. 2 goes to 3. 3 goes to 4, goes to 1. So I get 1, 2, 3, 1. Is that what I wanted? Not quite. Let's keep that in mind, though, is that if I compose, so if I try this way, maybe I'll need 1, 2, 3. I might have to compose that with something too. So let's keep that in mind, but let's try the other way and see what happens. 2, 3, 4, composed with 1, 2, 4. In this case, 1 is going to go to 2. 2 is going to go to 3. So 1 goes to 3. 3 goes to 4. Because 3 goes nowhere, then 3 goes to 4. So we're done. And then 4 goes to 1. So we close that off. And so we get 1, 3, 4. So that's not quite right either. So we're going to have to get more complicated and use a couple of these. And so, sorry, go ahead. So if I wanted to, I could turn this into 1, 2, 1, 4. One goes to, nope, sorry, the other way. So I could rewrite 1, 2, 4 as 1, 2, 1, 4. So I have the composition of just 2 cycles. That's possible. I'm not sure if that's, but then this one's going to be 3. I'm not sure if that's going to be more or less complicated, to be honest, though. It's worth mentioning. What did we get? We got, just as a note, we now have 1, 2, 3, and we also have 1, 3, 4 were our options, weren't they? Or was it? Yeah, that's right. I'm just pointing out, because we got these are now new things that we can compose to try to get this out. So we can think about, can I compose these, any one of these two together with any one of these to see what we're going to get out? And so I'm going to think, well, I need to get 1 goes to 2. So if I take this one with this one, I would go 1 goes to 3, 3 goes to 2. So 2 ends up there, but then 2 would end up at 3. So let's try 1 goes to 2, 2 goes to 1. That's not going to work. And so 2 goes to 4, 4 goes to 1. So maybe I can try these two together. Let's see what happens. 1, 3, 4, composed with 1, 2, 4. 1 goes to 2. So 1 goes to 2, and then 2 goes nowhere, right? And so then if I start with 2, 2 goes to 4, 4 goes to 1, so 1 goes to 2. If I start with 3, 3 goes nowhere, then 3 goes to 4. And then if I start with 4, 4 goes to 1, 1 goes to 3, so 4 goes to 3. So if I take 1, 3, 4 and compose with 1, 2, 4, I get 1, 2, 3, 4. Now notice that we were able to get this one by composing these two. So I actually had to use 3 of these things in all. So one of each, and then 2 of one of these and 1 of the other. And then I was finally able to compose it and able to get out my 1, 2, 3, 4. So it's not always as straightforward, just compose 2 at a time or compose them together in some direction and get it out. You might have to do some more work. And so I'm taking these and I'm combining them. And now how did I do that is, or get this one, is a lot of trial and error and guessing until, hey, look, it worked out. But because it worked out, we know that this is an element of this. Therefore, this group is a subgroup of this group. And since we've shown both directions now, we get that these two are indeed the same thing. So it's not always easy. I don't think this class is always easy on you guys, but that's kind of the point. That's what you would have to do. And so you mentioned making a Cayley table. A Cayley table would be helpful because you could do these compositions faster, but then you have to do all the compositions. So if you would like to, you're welcome to, and then you kind of say, okay, well, how would I get this out? And then you'd write that down as this is how I get this out, is by composing these things. Does that make sense, everybody? So to do it good enough is lots of experience, and even with lots of experience, it's still a lot of trial and error. And so I've tried to tell you guys, there's nothing wrong with getting things wrong a few times here in this class. That's kind of the point of the class, is that you will get it wrong a bunch of times. You just hope that, and eventually in the end, you can actually show what you're looking for. You just have to set it up so that you can see it correctly. Can you guys not hear me? Okay, it's just someone in the chat said no one can hear me, and I have to fix my mic. Yes, I am muted in Discord on purpose. Well, they have to be if they're typing in YouTube. All right, thank you, Jay. Thank you, Abel. I appreciate it, guys. Um, so just pointing out, if you guys are listening in Discord, I have it muted in Discord because otherwise there's a delay and you hear me talking twice, and I did that during the testing one, and it was kind of annoying. So I just turned off my Discord so you can't hear me there. You can only hear me through YouTube. But if my mic does go out, which happened earlier today, please tell me so that I can try to fix it as quickly as possible. And I apologize for any inconvenience that causes. I know this is a new experience for most of us, so hopefully we can make the best of it we can. All right. The next thing we're getting to here is direct products. I am going to leave that for next time. We're getting close to the end of the class period. So I'm just going to say thank you guys for joining me. I would go ahead and start looking at some of the homework. I will officially assign it on Wednesday when we're done in class, but start looking ahead and getting used to working with compositions again, working with subgroups again. A 2-week break is just killer. So James, there is no homework due tonight. It won't be due to next week. Originally, we had one assigned tonight, but that was dependent on the fact that we had class week last week, but we didn't. So I did delete that one, although I don't think I deleted it till last night sometime. So there was no homework due tonight, but there will be some next week. But I would start looking at it today just to get used to using it again. Any other questions before I let you guys go? So I'm going to stick with the same test dates as are on the schedule, but I'm going to be giving you guys make-home exams, so I don't know if I'm going to assign it that day or have it due that day. I think likely I'll assign it that day and have it due the next class period type of thing. Although, let me think about that one. That's a great question. The only way I would do that is I'd have to be able to scan them and send them to you since no one's allowed to meet on campus. I can, if I make it into campus, I can try to scan that, but otherwise you can email me. You guys can see your scores, right? All right, so if you want to see your exam too, then email me and I will try to scan and send a copy within the next time I make it onto campus, so within a week. I haven't been going in at all since they were discouraging it. Any other questions? Yeah, that'll be it for today. So thank you guys, and I'll see you on Wednesday.